Hello and welcome to the Ways of Math. I'm your host, Dan the Math Man. Today we're going to continue our multi-part series on the Introduction to Sets. This is video 5. And in this video we're going to be doing Venn diagrams with two sets. So in this video we're going to describe what Venn diagrams are, and then the regions that are contained within the Venn diagrams, what they represent, and how to solve a problem using Venn diagrams. Okay, so let's begin. So a Venn diagram is a picture that gives a visual representation of the interaction of sets. Right? So it gives a visual representation of the elements of the set, especially in context to the universal set, and also how the sets interact with each other. So when we're dealing with set operations, things like unions and intersections and complements, the Venn diagram gives us a visual way of looking at what these things are, and gives us kind of a tool that allows us to verify certain things about sets and solve certain problems with sets in a much more visual way, rather than just dealing with the written out, whether it's roster form or set builder form, etc. Okay? So you can draw Venn diagrams in numerous ways, and using different shapes and sizes and things like that. You can do it with multiple sets. You can do it with one set or two sets or 5 sets. In this demonstration, we're just going to restrict it to 2 sets. And we'll use kind of the standard Venn diagram for 2 sets, which is this rectangular box, which represents the universal set, and these ellipses, which represent sets, say, supposedly A and B, right? So, or whatever we name these 2 sets. Okay, so this blue ellipse represents the elements in set A, so contained inside the circle, or inside this ellipse, are elements contained in A. Inside the red ellipse are elements contained in B, and then inside this rectangular box are elements contained in U. Okay, and as we see, though we break this down, we have multiple regions, okay, or different segments of this diagram, okay? And so we'll describe what those regions are. Now, a few key concepts to keep in mind is that each region of a Venn diagram could be empty, and they are disjoint. So they don't have to contain elements necessarily. When we set up a Venn diagram, we have to account for all possibilities. So, for example, A and B might have elements in common. They might not, which means region 2 would be empty. Or maybe A has elements, all the elements of A are actually in B, so everything in A is contained in B, in which case region 1 would be empty. Again, because we kind of see visually that this region 1 is outside of B, okay, but it's inside of A. So that might be empty, in which case A is a subset of B. Or possibly region 3 might be empty, right? So everything in B is actually contained in region 2, which is contained in A. So that means B is a subset of A. Okay, region 4 could be empty, which means that the universal set, actually every element in the universal set, is distributed into either A or B, or possibly both. Okay, so each one of these could be empty, but they are all disjoint, right? Because you can't both be inside of one of these circles or inside one of the sets, and also be outside, right? So like region 3 is outside of A, so we can't have elements in region 3 that are also elements in A. And we can't have elements in region 4 that are in A or B, because we can't both be inside either of these ellipses and outside at the same time. So we can't be inside the set, but also outside the set. Okay? So elements are not placed in multiple regions, otherwise it would be a contradiction, as we just described. An element would then be, if it's shared by multiple regions, would mean that it exists in 2 different and distinct, namely disjoint sets. So we're both inside the set and outside the set. So in order for a Venn diagram to be useful, we need to place each element into its appropriate region. Okay? So now we're going to more formally describe what does each region represent. So region 1, okay, which now keep in mind, I will add this, these regions aren't necessarily always ordered or numbered the same way, especially for bigger ones. This is just kind of the standard way we do it. So kind of the usual way that we set up the region numbering, which is always done with Roman numerals, or usually done with Roman numerals, is kind of left to right, top to bottom. So if we kind of imagine the sets being broken down like left to right, top to bottom, and then you almost always, in every way we set it up, it makes sense to have this set, this region that's outside of all of the sets we're talking about, to be the last region. Okay? But it can be, if it's set up with multiple sets, you might have these regions numbered in a slightly different way. Okay? But in this case, the way we have it set up, the region 1 we're talking about is this region 1 here, which, as we clearly see visually, it's elements that are in A, inside the red blue ellipse, named A, but outside of B. Right? So region 1 is in A, but outside of B. So elements in A, not elements in B. Formally, we write this as the intersection, right? So A intersect the complement of B, right? So inside of A and outside of B. Region 2, now this is in the overlap. So it's in both A and it's in B. So these are elements that are in the intersection. They're in both A and B, so elements that are in common with A and B. And we write that as the intersection, A intersect B. Region 3, similar to region 1, this is elements that are contained in the set B, but are outside of the set A, right? So inside this red ellipse, but outside of the blue ellipse. So inside set B, outside of set A. And we formally write that as the complement of A intersect B. Region 4, finally, is our last region. So that's visually outside of both of the ellipses. So it's outside of both sets A and B. But of course, every element is contained in the universal set because the universal set is all the elements we're dealing with for a particular context. So that's what goes in region 4. So it's everything in the universal set that are not already present in A or in B. And then formally, we can write that as the complement of the union of A and B. So everything in A or B, but then outside of it. So that's what the complement is everything outside of that. Okay. So you might ask, what exactly do we write in the regions, right? We've discussed what the regions are, but what do we actually write inside there? So how do we use the Venn diagrams? How do we construct the Venn diagram? Well, we could do this in a couple different ways. One way is to write the explicit elements in the appropriate region, right? So the explicit elements of A and the explicit elements of B and explicit elements of the universal set, we break it down into what goes in each one of these regions, and then we can explicitly write those, like kind of in roster form within each of those. Or we can write just the cardinality of each region, so how many elements are in each region. And which one we use depends on the situation. Normally for a lot of application problems, which we'll see more later, especially with bigger sets and larger quantity of sets, so number of sets, and with larger set sizes, a lot of times we use the cardinality. That's kind of what's more important. But in some situations, we actually do care about the individual elements, and that's when we'll use the explicit elements within each set, within each region. Okay? Again, keep in mind, every region is disjoint, right? So if we think in terms of cardinalities, right, like the second type of way to set up the Venn diagram, then the sum of each cardinality, as long as that's finite, is equal to the sum of the cardinality of the, is equal to the cardinality of the universal set, right? So back to this visual here. So if I sum up the number of elements in here, right? So I take the number of elements here, add it to the number of elements here, add it to the number of elements here, and add it to the number of elements here, I will always get, if this was constructed correctly, the number of elements inside the universal set, right? Because these are all disjoint. So we will never worry about double counting anything if we add up each individual region. Okay, so let's take a look at an example. So let the universal set be the positive integers from 1 to 10, right? So we have 1, 2, 3. Notice these ellipses. So this implies that we continue on the same pattern. So even though we don't write it, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's the universal set. Suppose we have two subsets of the universal set A and B. And we'll define A as being the set containing the elements 1, 3, 5, 7, 9. and B is the set containing the elements 2, 4, 5, 8, 9. Now we're going to determine the following. So we're going to perform these set operations, okay? And we're going to use Venn diagrams to do those. Okay, we want to determine the union of A and B, the intersection of A and B, the complement of B, and then also the complement of the intersection of A and B. Okay, so first we need to construct the Venn diagram. So now what we're going to do is we're going to construct our Venn diagram, okay? And we'll see more generally when we see a larger Venn diagrams, a kind of more solid approach, but you'll kind of see an idea of how we do it here. So we typically start with the innermost region and kind of spiral outward, okay, or kind of work our way out. So we start with the innermost region here, which is region 2. What elements are in both A and B, right? So we simply kind of traverse our way through set A. So we kind of count our way through the elements in A and see if any of those elements are also in B, right? So 1, for example, is not in B. 3 is not in B. 5 is in both A and B. So boom, 5 goes inside region 2. 7 is not in B. 9 is in B. So we see that 9 is also in both A and B. So that goes in the center there. Okay? Now what we would normally do is then kind of X these out, right? So we don't double count them, especially for bigger sets. It's important to kind of keep track. These are relatively small. They're not too bad. But once we put 5 and 9 in here, they can't go in any other region. Okay, so 5 and 9 are in here, and now we can't place them anywhere else. So now let's say we move to region 1. So region 1 is the set of elements in A that are outside of B, so they're not also in B. Well, we've already crossed out 5 and 9, so we know that everything left in A is not in B. So the elements 1, 3, 7 are the elements that go in region 1 here. Okay, and again, we would kind of imagine crossing those out both in this set and in the universal set. So we know what we've counted already, what we've placed, and what we have not placed. And then similarly, we move to set B, right? So this region 3 is what's in B that's not already in A. So we already see that 5 and 9 were in A, so therefore 2, 4, 8 must be the elements that are outside of A. So 2, 4, 8 are in B, but not in A, so therefore they go in region 3 here. You see 2, 4, 8 there. So again, we've already accounted for a lot of these, right? We have 1, 2, 3, 4, 5, 7, 8, and 9 have already been accounted for in these 3 regions. So now what's left? Well, if 1 is gone and 2 is gone, then 3, 4, 5. Notice 6 wasn't placed up here. So 6 is an element in the universal set that's not in either A or B. So 6 goes out here in region 4. And then we have 7, 8, 9 inside here, but notice 10 is not in A or B. So then 10 also goes out here. So now we've accounted for all of our elements in the universal set. So as a check, we can count through to make sure that we've placed all 10 elements from the universal set in their appropriate regions. So we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all the elements that have been placed. Nothing was placed in multiple regions. So we have completed our construction. Now we're going to use this construction to answer the questions that we had on the previous slide. So we want to answer the union A and B. So A union B, right? So that's everything that's either in A or in B, right, from our definition. So that's going to be everything in regions 1, 2, and 3. So we see highlighted here regions 1, 2, and 3. So we now that we've seen visually what these are, now we just simply count the elements. So we place these elements in the set, and those are what's going to be in the union. So we have 1, 2, 3, 4, 5, 7, 8, and 9 that go into our answer here. So that A union B is then that set there. Okay, so again, we're starting to kind of see the power of these Venn diagrams on how we can visually see these set operations, and we can answer questions a little bit quicker once we construct our Venn diagram. All right, let's go on to problem 2. So Here we want to find the intersection of A and B. So what's in both A and B? Again, we highlight the region that we're talking about. So the intersection of A and B is what's in region 2, the elements in both A and B. Right? And so we see there are only 2 elements there, 5, 9. So that's our answer. Our set is the elements 5 and 9. Okay? Pretty straightforward, hopefully. Again, this visual representation is very useful. Okay, now the complement of B, right? Again, from our definition, the complement of B is everything in the universal set except for B, right? So we highlight everything outside of B here, right? So as we see again in pink, everything outside of B is highlighted, okay? Which accounts for regions 1 and region 4. So we simply count the elements in regions 1 and 4 and list them. So 1, 3, 6, 7, and 10. So those are the elements in the complement of B. 1, 3, 6, 7, 10. Okay? All right, let's take a look at the final example here. So for this one, right, think order of operations, because we have order of operations with arithmetic. We also have them with sets, so we work within the parentheses. So we're going to first compute what A intersect B is. Well, we already did that. A intersect B is the region 2, right? As we see here in blue, that's our region 2. So we have the elements 5, 9 there. Now we want the complement of region 2. So remember, the complement is everything in the universal set except for that set. So everything outside of this region, if we highlight those, as we see in pink, that's regions 1, 3, and 4. That's the complement of region 2. So then we list all the elements in 1, 3, and 4 to get our final answer. 1, 2, 3, 4, 6, 7, 8, and 10. And that's our final answer there. Okay. I hope you enjoyed this video on this introduction to Venn diagrams using 2 sets. Please be sure to subscribe and leave any comments or suggestions in the comment box below. Also, so if you subscribe, right, you can be notified of future videos. There will be more videos in this set. And I hope you enjoyed. Thank you for watching. Have a wonderful math-filled